Darshana Bhadra, the assistant editor of OEM Update magazine, and I'd like to welcome you to a technology session on Digital Twin, the doorway to smart manufacturing, powered by Kennametal India Limited. So, throwing some light on the topic, we understand that the manufacturing landscape is becoming more dynamic with the adoption of cloud-enabled and connected data platforms that are reshaping in-part production. These platforms integrate data from various standalone sources for real-time decision making and supporting data-driven decisions. At the same time, customer expectations continue to change. From the need to machine complex 5-axis components with high machinability indices and tight tolerances to the demand for optimized machining strategies that improve process efficiency, reduce waste, control costs, and boost productivity. Here, Kennametal has introduced an innovative solution-driven approach built around the digital twin concept to handle this issue. This version model replicates physical products with high accuracy, allowing engineers and planners to stimulate, test, and refine processes well before the physical production begins. By identifying potential issues early, manufacturers can avoid costly downtime and make better, faster decisions on the shop floor. Kennametal's digital twin technology enables complete visualization of the machining operations, accurate estimation of cycle times and tool wear, and the generation of executable NC nodes. It is quite simply a blueprint for smart machining and a gateway to the future of manufacturing. And to explain this technology in detail, I invite Mr. Karthik Raman, who is the General Manager of Product Management at Kennametal India. Mr. Raman has over 2 decades of rich experience in metalworking industry, and he has played a huge role in developing products that address complex machining challenges, particularly in the aerospace sector. A mechanical engineer with a postgraduate degree in management, Karthik has a strong background in analytics, strategic road mapping, new product development, and product lifecycle management. So, Mr. Raman, please go ahead with your presentation.
Thank you, Darshana. This topic today is about smart manufacturing and how digital twin and AI. I will talk about AI also a little bit towards the end of my presentation because that is also going to shape a lot the way we do things in the next few years, right? So the agenda, this is the flow I have set for today's presentation. So we'll just talk a little bit about who we are, what we do, Kennametal as a company. And then we will deep dive into the topic, which is for today's webinar, Digital Twin and AI, the doorway to smart manufacturing. So with that, I will straight away get into the subject. So one of our key objective in Kennametal is to transform the way things are built around us, whether it is manufacturing, whether it is product lifecycle management. There are a lot of changes that are happening around us, right? So we are very, we take a good view of these changes that are happening around us, and we try to build things to make life easy for our customers. So that's where we are focusing a lot in that aspect, and we will continue to focus in that direction in the coming years too. So as a company, we are about 85 years plus in operation. So we have a very strong history in material science. Starting from the year 1938, we have been part of providing a lot of high-end engineering solutions to our customers. And we broadly cater to these 5 segments. So general engineering, energy, aerospace and defense, transportation, and earthworks. So in terms of our financials, we are about a $2 billion company, and worldwide we have about 8,400 employees. And we are present in nearly 100 countries, serving our customers, helping them to transform manufacturing solutions. So I spoke about the material science aspect of our organization, right? So recent times we are also doing a lot of work around additive manufacturing. And that gives us an edge in terms of how we build things, right? So how we provide a differentiated solution to our customers. So that comes with the rich experience and heritage and legacy that we have. And from right from the powder to the finished part, we leverage comprehensive additive manufacturing capabilities to drive and deliver innovation, performance, and bring value to our customers. So some of these examples are shown here. I'm not going to talk in detail about these examples, but be it the Edison Award, uh, which is the most renowned award for innovation in the industrial engineering space. So we recently also bagged awards for the Ken Ionic technology that we introduced with some of our product lines. And then the additive manufacturing technology that we leverage in building some of our product lines like modular drills and some of the complex custom solutions that we provide to customers. And also, not only that, we also use a lot of AI-driven, you know, uh, tools and techniques to optimize the supply chain and logistics aspects of it. So we have the operations worldwide. We have more than 40 locations where we operate as a company. So end of the day, we work towards driving benefits to the stakeholders, be it customers, be it employees, be it our own shareholders, right? So as far as customers are concerned, they they actually care a lot about the quality, about the product performance, about the innovation, about the new technologies that we bring in, and the logistics and delivery aspects of it. If you talk about the employees, we have a very highly engaged employees working with us, and many of them, they work in the core R&D sectors who bring a lot of value in terms of driving innovation and building new products for our customers. And in terms of shareholders, we always think about driving the long-term value for them in terms of their growth. So these are some of the examples of our innovation culture. So just for example, FY24, we introduced more than 20 plus new products into the market. So we have about 22 engineering hubs operating worldwide. We have 1,800 active patents and 500 plus doctoral and global scientists working with us. And we have the RD&D centers operating out of US, Germany, and India. So whether it is electric vehicle, whether it is some space mission activities, which I'm going to talk a little bit in the next slide, we bring in a lot of value to our customers in the way we do things differently. So this is another example where when the rover landed in Mars, it was the tool that it used was made from the Kennametal carbide. So the Mars planet, we all know, we are like millions of light years away from that planet. The topography of the planet and the soil, the nature of the elements in that planet is hardly known, right? So we actually did a lot of deep work into that aspect. So the rover got finally equipped with a tool that had the Kennametal K92 grade, which really helped to kind of drill deep into the soil and the surface of Mars, and that finally got used to analyze those samples. Without the experience of additive manufacturing, 3D printing, having a very focused engineering design approach, it's really not possible. So here is a case where the customer was really struggling about doing things differently. I mean, he had a very low power machine and spindle lines, but he wanted to actually produce bigger bow sizes. So wherein he wanted the tools to be weighed of certain mass, which seemed practically impossible given those conditions. That is where our RD&D engineers came up with innovative ideas, wherein we literally printed this tool through 3D, and then we reduced the weight in such a way that finally this tool customer could use in those existing machines, low power spindles, and achieve the required tolerance for the stator board of the EV motor housing. So like that, I can go on listing. So if you're seeing us, you can join us, through any of these kind of social media channels, be it Facebook, LinkedIn, Instagram. We are present, YouTube, and all the new product launches we bring in time to time in those channels, and you can watch out for more updates from us. So let's get started with the digital twin topic, the doorway to smart manufacturing. So before I start with the digital twin, I would like to give a small heads up in terms of the realm of AI, right? So this particular picture, I'm sure many of you would have seen, and AI is a very large, all-encompassing term which hosts everything, right? So a subset of AI is machine learning, and the subset of machine learning is neural networks and deep learning too. So what is AI? AI is the machine's ability to mimic human intelligence. So someday or the other, the progress will happen where most of the repetitive operations will be taken care by machines. And how this will be driven is through machine learning. So where the machines will have the ability to read data and patterns, learn and improve performance over time. So this is very critical, right? So um, for millions of years, humans, we have actually evolved as species in terms of our own experiences and learning from some of the things what we did in the past. When machines can imitate that and be able to learn, from the data, from the patterns, it is really throwing up a new realm of life, I would say, in front of us. So when I have to really talk about manufacturing, so AI assisted CAM, that is going to be the future. It is not there still, but many of the CAM companies and the tooling partners, they are working very closely to enable some of those options available for the customers, which will utilize artificial intelligence and machine learning to enhance various aspects of manufacturing, whether it is process planning, whether it is design engineering, whether it is simulation, or even, for example, prototyping, production, quality control, you name a field. This is going to have a huge impact in the coming days. So the advantage what customers will get is it helps to streamline the operations, and it will improve the accuracy and enable kind of adaptive manufacturing practices, right? So that is the ultimate goal, is to attain. We call it as level 5 autonomous machining, but that is today's context, you can say it is little far-fetched, but I'll say that, in it is not too long till we figure out, a day will come where most of these operations, which are repetitive in nature, will be programmed by machines, including CAM cycles. So a subset of machine learning is neural networks. So this is how the the AI will build models using neural networks to learn from the data. And the deep aspect of AI is called deep learning. It is nothing but, I mean, if I have to give an analogy, it is very similar to our brain. You have the connected nodes, you have those transmitters, receivers, which can simulate, analyze, learn from large scale data structures. And also it will have speech and image recognition capabilities that almost it makes like human, right? So that is a small intro on AI and how that is going to transform manufacturing along with CAM advancements that we are talking about. So just to give you some heads up in terms of the evolution of CNC machines and how the CNC AI technology is going to transform the world. So I've just put some information here. Initially, when we started, it was in the year 1949 in MIT labs, a group of scientists, they started working with NC machines only for their prototype development. And subsequently in late 1960s, then they integrated those NC machines with certain, uh, you know, kind of primitive computers and digital electronics with which commercial CNCs got launched in the year 1960. In the year 1960s, that is where the commercialization of the CNC machines started. And then towards the 1980s, more emphasis was given to the graphical user interface, and that is where it allowed the users to input G codes and M codes, and also it helped to through Linux-based operating systems, it helped the users to input some of these data. But still, it was a little primitive at that point in time till the evolution of CAD/CAM took place in the uh, late 1980s or early 1990s. That is where more feature-driven CAD/CAM models started evolving, and towards the end of 2000, that is where full-blown five-axis CAD/CAM systems started developing, and it really helped complex machining processes. And today, if you see, there is a development. We talked about the digital twin, right? So digital twin, we will see that a little bit more in detail in the next slide, is getting introduced, and which is also providing real-time feedback on the part quality and to identify errors, collision check, automatic toolpath generation. A lot of things, today's systems are capable of. And what can happen in future, if you ask me, like 5 years or 10 years down the line, which really nobody can predict, but we expect CAM systems will become even more intelligent with the integration of Gen AI, and as I said, some of the repetitive components will get auto-programmed, and it will be able to identify and learn from the real-time data. People will start monitoring more in detail about the tool load, the tool life, and adaptive machining, optimization, and it will continuously evolve, right? So when these systems behave in a way that it can learn and optimize themselves without the need of human intervention, and that is where the whole game starts to change. So let's see what is a digital twin. Digital twin is the kind of hot topic of this webinar. So if I have to really, talk about this in a layman's term, it is a digital replica of a physical asset or an object or a system or process, contextualized in a digital version of its environment. So why we need to have these kind of digital twins? So digital twins can help organization in multiple ways. One is it can simulate the real life situations and their outcomes. So imagine, let's say we are building a project, and it's important that we simulate and see what kind of possible errors that can come, or how I can optimize some of the roadblocks that I may face during the execution time, right? So that way it helps better visibility to the outcomes, ultimately allowing the users to make better decisions, right? And it is classified into broad categories. The data twin and the systems twin. There are multiple levels. We can go on. Ultimately, what it means is a digital twin is a kind of a physical representation, is a digital representation of a physical object, uh, in order to make uh, meaningful decisions, right? Also, it helps the process planners and engineers to identify any bottlenecks, failures that we may foresee before the actual, uh, productionization of the part. So in manufacturing, if I have to little bit talk about the digital twin in manufacturing, so complex multi-axis machine require a deep knowledge and understanding of fixtures, cutting tool, process, and programming. So finally, the case studies what I'm going to share later on, you will see the entire configuration of the shop floor, including the machine fixture. Everything is built and then it is programmed and it is delivered, so that we were able to visualize a lot of things even before actually we started cutting the part. So that way it helps a lot. So finally, it's a replica also help to translate machining results to performance by allowing for a precise estimation of chip loss, cycle time, executable NC codes, right? So lot of functionalities you can build in with the digital twin. So end of the day, you know, every company works for bottom line, improving their reduce errors, improve the customer experience. Finally, as engineers and process planners, we should be able to take better decisions on the shop floor with these kind of advanced tools. So let's see some real life customer testimonials. So this is actually the nozzle guided vane. One of our aerospace customer who was into the production of this part, and he was cutting the part more than I think 90 plus hours, nearly 90 hours to 100 hours was the cycle time of this part. If you see the part, it is little complex, in the sense, you can see these are like closed veins, impellers, and the approach is not there, and you have to actually approach this part uh, with a multi-axis configuration, and very expensive part, expensive material, Inconel 718, which is high nickel alloy, uh, heat resistant alloy, which offers a lot of resistance to cut. And because of all these aspects, he also wanted first time right, no rejection. So he had a very clear expectations in terms of what he was doing and what he wanted. And to add fuel to the fire, the profile tolerances were very tight, and he wanted to achieve all the profile vein tolerances within zero point 0.1 mm. And it was kind of 5-axis simultaneous machining. So what we did was that, this is the input of the part, and this is the output you can see. And it is like the outer diameter is around 325 mm after finishing, and the inner diameter is 187 mm. So it is in the HP stage or the nozzle stage of the aero engine, and it's a very difficult profile, right? So very closed blade veins, and we have to use different types of tools to engage the profile from various directions. For example, I'll just play this video. So you can see here it's a DMU 65 monoblock, and we kind of simulated the whole machining environment where you can see the complete orientation of the part, including its fixtures. And as it starts machining the 5-axis uh, vanes, we have to be mindful of the collisions, the gouges, and the maximum, you know, penetration of the tool into the workpiece to minimize the cycle time. And some of these kind of closed loop machining processes, what we adopted, and with a completely different type of tool, gave us a lot of advantage. So this is what I was, friends, actually today's thing. This is one of the examples where we could simulate the whole thing and see those process uh, nuggets where it can be improved even before you start cutting the part. In terms of, you can calculate multiple things. You can calculate the tool load, you can calculate the torque, you can calculate the sequence of machining operations, how it should be done, because the part is expensive and there is no second part available to experiment, right? So that is where we need to be extremely careful in terms of doing things right first time. And also, not just the machining, also these kind of coolant drain flow gaps also we ensured we gave this heads up information to the customer, and based on that, so that these chips, whatever gets accumulated inside, it can easily get drained out with the coolant pressure once we provide these kind of channels in the fixture. So we also worked very closely with the customer and did a lot of improvement, not just to the tool, not just to the process, but also to these kind of work holding elements and to the machines, the way it was used. So finally, we were able to reduce the cut time from whatever it was, like 90 plus hours to 71 hours, thereby contributing 26% reduction in the cycle time. And not just reduction in terms of the cycle time, I would say, but the assurance of the process, right? Because the safety and the security of the process is more important in these kind of components, because customer will never take a second chance, because these are expensive parts, and it becomes extremely critical for us to deliver the right part right first time. And all the quality parameters in terms of the profile tolerance, surface finish, everything was met, and finally we left a happy customer. So that was one example of digital twin where we kind of replicated or we simulated the whole uh, condition even before we actually got into the machine. This is a second example where you talk about there's again a very complex profile on stainless steel blade. So this was again on a PS95 Makino machine where customer was planning to achieve a very tight tolerance and also the cycle time. There were challenges, but we were kind of confident enough to overcome these challenges with the concepts that we had. So these are some of the videos I would like to play, before, so that some of the machining strategies and some of the simulations. I have not shown here the power, torque, and the load characteristics. Those things can be directly measured from the machine controllers, and that will also give us a lot of information in terms of um, how the tools in cut can be optimized further. So those kind of things also we did in this case, and we have great product strength in terms of machining these kind of materials, and that is where the Harvey series of end mills, it scores. It maximizes the advantage with its greatest and the latest coating and the configuration of these end mills. So these are again some more simulations in terms of the way the whole assembly, uh, the kinematics of the blade of the blade, the way it underwent the machining process. And the fourth axis synchronization is extremely important here. So that is where we ensured there are no errors in terms of the indexation of these fourth axis components. Simulation, so you can see the total machine environment. So which means we had the kinematics of the machine, and also we ensured we had the right acceleration, deceleration, speed limits of the machine, which really helped us to program the part right first time. And whatever we did through this, and when we did the input of these codes into the actual machining setup, we were able to achieve 98 to 98.5% of what we had predicted before. So the scope for error was a little less or very less, I would say. And that all this visibility comes because of the digital twin and the process planning experience that Kennametal engineers they have. So here, if I have to give you a heads up in terms of what did we contribute? So it was 93 minutes earlier. So from there we came down to 47 minutes. So just almost you can say about 50% reduction in the overall cycle time. Not just that, improved process control, process security, good surface finish, and size tolerance, which was delivered to the customer. So for today's webinar, I have actually picked and chosen these kind of components, which are very intricate in terms of machining. I showed you the closed blade vane, which goes into the rocket engines and some of the high thrust aero engines. Then we saw the blade, which is again a 5-axis component. And now this is the third example, which I will talk on the digital twin, which is a blisk, which is the IBR. So again, here, if you see the material, it is 990. We also machine 90115, which is even more difficult than this. But here, if you see, it is about 60% nickel, which makes this material highly abrasive and extremely sticky. If we don't use the right parameters, even if there is an marginal error of 5-10%, and it is going to be difficult. It's a DMU 65 monoblock 5-axis machine, and the input and the output configuration of the component is clearly shown, and some of the machine axis details and the torque and the RPMs are given here. So again, here it's an IBR, and I'll just play this cam simulation video. And how did we do this? So again, the profile tolerance on these impellers, on these blades, are extremely important, and that is where the machining process sequence, and initially when the material is solid, we can be a little bit more aggressive. But as you start scooping in, and as the chip loss increases, and the veins become thinner and thinner, and that is where the problem starts, right? So we should be able to operate uh, with the right parameters and the right tool geometries, not to exert too much of force and cutting load onto the veins, but at the same time ensure maximum engagement, and so that the material removal rate increases and we don't end up taking too much of cycle time for these kind of parts. So that was the third example. And again, here with the digital twin, with the complete uh, visualization of the machining dynamics, the machine and its dynamic behavior, with the visualization, the way the component is held in the fixture, and the tools and the process sequence that we had. And along with that, the power and the torque calculations and the individual tool load calculations. So all these things gave a lot of information in terms of how we can optimize this part and how we can actually deliver better results for our customers. So in this case, again, from 21 hours, we came down to 11 hours and successfully delivered the part with the right quantity characteristics and process. We are doing and we are delivering, which is good, which is great. But how this is going to transform in the future, and that makes this webinar even more interesting, right? So what will happen is, you know, we are also working in terms of how do we actually tap into the real-time load and real-time tool life monitoring on machines, right? So you can have data centers, you can have a lot of feedback loops that can get created. uh, you know once you completely machine the part, and then you can also learn, you can set your limits, and then you can operate and see how you can, uh, if it exceeds the limit, it can throw up a caution, and then it prevents a kind of a collision, or you can avoid some unwanted situations in terms of machine collisions and overloads, etc. Similarly, it helps a lot. AI assisted CAM will help a lot in terms of optimizing the machining strategy. So since this has got the ML aspect of the AI, which we saw, it is able to learn from the data that it is generating, right? So somewhere, it can, if it senses slightly lower load, and that is how the sequence of operation has been for, let's say, 40, 50 parts. And over a period of time, it can be taught back to the CAM engine, uh, from this part onwards, probably you can be a little aggressive here because you're not exceeding the load. And so far, whatever parts we have machined, which has come okay, and we are within the limits. So those kind of feedback loops can be created, which will make the CAM to learn. And that again brings us to the third topic, which is adaptive machining. So you have a lot of haircut time, and how will you optimize? As we start machining more and more parts, we also evolve over a period of time, right? So that learning curve can be shortened with the power of AI. That is what we are saying. And some of the repetitive parts can also be programmed. Nowadays, there are a lot of feature detection CAM systems available, and many companies, they are working in that direction in terms of if you upload a part, and it actually figures out all the machining areas, and then there is an automatic process selection, tool selection. Even there is a built-in intelligence, let's say, to an extent, if it is a threaded hole, if there's a tapping, what kind of pre-drill I should choose, and accordingly how I should plan that particular threading operation. There is a lot of uh, intelligence that is being given to develop these kind of systems nowadays. And then this is what I was telling you. I mean, in terms of any adverse event and machine risk avoidance, AI can be an extremely handy tool which can help us optimize the machining strategies and maintaining the tool load and performance. The last but not the least, it will help us in terms of driving a lot of Kaizen improvements, continuous learning aspects, and this is going to definitely revolutionize the world in the near future. So, what are the benefits to the customer? These are some of the features. These are some of the aspects that we saw. Definitely, it will help customers to accelerate time to market, right? And that is where many of our customers, they struggle. They plan, and but for some XYZ reasons, they are unable to deliver the part on time. So these kind of CAM assisted or AI assisted CAM, it will definitely help to accelerate that process. It will help in optimization of the manufacturing costs, because you will foresee all these errors in advance, and then we will be in a better position to take certain calculated steps approach towards those errors. And that will also help us in terms of optimizing the cost and the manufacturing strategy. And finally, it will improve the overall process efficiency and the profits for the organization. With the AI assisted machine monitorings, we can utilize the best capability of the machine. We can utilize the machine to its fullest extent. And also, we can reduce a lot of iterations and then shorten the learning curve. I spoke about this in the previous slide. And finally, secure the operational effectiveness by real time uh, monitoring, be it load, be it tool life, and also prevent any adverse event happening. And finally, it'll go to a stage. This is like level one. Whatever I'm talking today, it is a kind of level one, or between level one to level two, right? But days are not far off where people will achieve level five autonomous machining with very less human intervention, I would say, where the CAM systems and the robots will play a bigger role in the manufacturing arena. So that brings me to the end of my presentation, folks. So thank you very much for your patience listening, and I'm very happy. I can take some questions if you have something. Thank you.
Thank you, Raman sir, for sharing and highlighting the significance of digital twin. It indeed is a doorway to smart manufacturing. So we have few questions. First is from Nemish Chauhan. He's asking which technology you have used to set up the digital twin for your machines.
Uh, I mean, this is a little confidential information. I can talk about the architecture a little later, but right now, maybe we can pause this question. There are a lot of
Okay.
technologies. There are a lot of technologies, but what we are adopting right now is a very different approach.
Okay. And he's also asking who are the vendors providing AI assisted CAM solutions?
I mean, all the CAM companies today, they are evolving in some form or the other, right? So I don't want to name and pick up one particular company or partner, but there are a lot of companies today. They actually do this kind of developments. So you know the companies who are operating in the market. There are good CAM companies who can actually provide you a lot of information on this.
Another question is how do users handle authentication, encryption, and access control for digital twin environments, especially with multi-tenant cloud deployments? Basically, they are asking about the cyber security.
Yeah, see, that is an important element because you know we have, we have the network which is fully secure, and it has got the firewalls. So whatever data transfer that we do, it is 100% secure. It is fully encrypted, and then it is loaded onto the machine. So um, I need to really check with my IT folks in terms of what tenants they use to enable these kind of process security. But at this point in time, I'm not an IT expert, so I I I don't think I'll be in a position to answer that question. But definitely, I'll get back to you on that.
Thank you so much. So next question is, did you come across implementation challenges while deploying digital twin technology for complex components like NGB and BLISC, and how did you overcome those challenges?
See, many, right? The challenges are inevitable. It is not whatever I have showed you in that 10, 15 slides. It was not achieved in the first shot. That is where the digital twin, comes into the picture, and it gives you the complete clarity in terms of how these systems are going to operate. How the real life scenario is going to be, right? So you run through a lot of virtual simulations. You check, you create a lot of checks and balances. You check the process again and again. Let's say you have sequence of operations, how these tools and processes are going to flow one after the other. Just to answer that question, yeah, we had faced a lot of challenges, but that is where the digital twin helps us to visualize all these elements, the nitty-gritties and the difficulties that we will face in advance, and then take those corrective measures, be it process, be it fixtures, be it machines, be it programs, be it tools, be it linkages of operations, be it connected machines, everywhere, right?
Okay. Ms. Tamani is also asking, are there any ROI improvements that your customers have realized after adopting digital twin and AI assisted machining?
Yes. So, I have shown a lot of metrics, right? So I have shown the cycle time improvement from 100 hours to 70 hours, and from 120 minutes to 37 minutes. I have spoken about all these things. So it means a lot to customer because these 5-axis machines, they are damn expensive. And more than that, the parts, these are extremely complex parts. These are high value, raw materials. And if we are able to save, let's say 20%, 30% of their cycle time, and if we are able to improve the process, it means a lot to them. It means a lot to them. So that is where, the digital twin and the AI assisted CAM technologies are going to shape the world and future.
Oh, thank you. So we have next question from Mr. Gobinathan. He's asking for machining with more number of tools is used in VMC, fourth axis, like approx 30 tools, and they consist of taps, drill, milling. So how does Kennametal support to reduce the cycle time?
So, see, I don't want to sound uh, very optimistic or uh, you know logical or illogical here. But the thing is, these kind of specific questions, we have to actually go through your part. We have to go through the operation. Sometimes, we have to do completely different. We may not suggest the way, you're doing right now. So we have to take a look, we have to take a fresh look at the part, and if that component and the volume of production merits maybe a different machine, maybe a 5-axis machine, or maybe a different approach, why not, right? So I don't want to comment right now, okay, we can reduce 40 tools to 30 tools or 20 tools, something like that. But what we will do is we will give a good look, we'll give a good look at the current, the way, the manner in which the parts are getting manufactured, and the volume of production, and your future expectations in terms of the quality and the production metrics. And then we will take a very calculated call and approach in terms of how this can be done efficiently, which will save a lot of time and money for our customers.
So you're open for customization.
Exactly.
Okay. They're asking what approaches are used for detection and root cause analysis within the digital twin framework.
Yep.
Like if there is any issue with the digital twin framework, what can be done?
So we have the collision detection softwares which will throw up information in terms of where we are exceeding the limits, or where we need to work in terms of the change in process. And we do have a lot of calculations around the engagement of the tool and the load that it creates on the part. So no, that also gives a lot of room for improvement, when we plan the process. And last but not the least, besides verification softwares, besides all these calculations that we perform, when we take a good look at the entire process, which includes the machine, and which includes, we have the entire kinematics of the machine itself, right? I mean, we know the limits of the machine and where it will give alarm, where are the sweet spots of the machine, how we can work within the sweet spot of the machine. And then also, in terms of the component holding and the other process, we work with the tools and stuff like that. When you visualize the full setup, when it presents a kind of holistic view to you with the kind of simulation and the digital twin, and that is where the rooms of error becomes very less, and you don't end up making simple errors. For example, I mean, sometimes there can be errors. I'm not saying it is 100% foolproof and you will come out in flying colors. No, there can be 1 or 2% of errors, but that is more in terms of improvement, right? Not in terms of uh, you know collision or something, uh, kind of untoward situation that happened and the part gets scrapped. No. So I hope that answers your question.
So it is, can digital twins be leveraged for advanced quality control in aerospace, such as automated defect detection in large structures, or predicting
That is the
potential deviations in manufacturing tolerances?
Yeah,
Yes,
so that is
please.
the next step. That is also the next step, to bring in that measurement capabilities, into the digital twin environment. We are also working on that. Um, so that is still in a kind of little initial stage. But what I can tell you is, that is the next level. So once the part is done, and how will you seamlessly transfer the measurement coordinates of the part to the inspection equipment, and without any data loss, how will you inspect and qualify the part very quickly, right? So that can be looped in, that can be definitely done. But right now the cam systems are still evolving, and as I said, days are not far off where you will bring in those kind of meteorological aspects into the cam systems.
Says, do you see predictive maintenance and automated corrective actions become fully autonomous in future?
Yes and no, but when we achieve the level 5 autonomous machining, which is the kind of the final stage of the evolution in terms of manufacturing, a lot of things can be automated, right? So the industry 5.0, where you have the collaboration between the robots, and they will be able to sense data, they will be able to exchange information, they will be able to do the inspection and inline or offline inspections, and those datas will get shared across multiple domains. And if something is going wrong, let's say in terms of this machine spindle bearing, those kind of things also can be predicted in advance. Okay, this machine spindle bearing can only run for next 1,000 hours. At least that information can be given to the user in advance, so that he can prepare um, you know the spare parts and other stuffs readily available when those elements due for change. It's possible, but if you ask me whether the systems and the connected environments are developed to handle today, no, it's not. There are few model factories within Kennametal, but we are working towards level 5 autonomous machining. So it's a journey, I would say.
So thank you, Karthik sir and Kennametal, for steering the discussion on digital twin, the doorway to smart manufacturing. I hope our delegates enjoyed the session thoroughly.
Thank you. Wish you all a nice day. Bye-bye.